All right, so let's see. It talks about the Lorenz curve, L of x, gives the proportion of the total income earned by the lowest proportion x of the population. For example, L at 0.9 would equal 0.55, which would mean the poorest 90% earn 55% of the total income. Okay, so how would we interpret L of 0.25 equals 0.1? All right, so the poorest 25% earn 10% of the total income. Okay, so if everyone earned exactly the same amount of money, okay, what would L at 0.3 be? Yeah, it'd be 30%, 0.3. Okay, so they'd be equal to each other. L of 0.65 would equal 0.65. Okay, so that's all that's saying. All right. So let's look at number 2. So the curve y equals x represents total income equality. So on that graph, we can see the line y equals x. The Lorenz function for a particular country, you gotta stop, is given by L of x equals 0.25x plus 0.75x to the 11th. What does the area between these functions, region A, tell you about the country's wealth distribution? What do we think? Yeah, okay. Basically, if we're thinking about that rectangle, it tells me that the bigger the area of the rectangle, the greater the inequality of the wealth. Okay, so the bigger the rectangle, the greater the wealth inequality. So for number 3, it says give an estimate for the total area of region A. So of that rectangle that we see, okay, what would be an area that's too low?
Wait, is it?
0.01.
Yeah, 0.01. So we're just talking about this rectangle.
Okay. Oh, I'm talking about the region A.
Yeah, which is this thing? Oh, or region A. Yes, sorry, hold on. Yeah, here's region A. Okay. So, and then what would be a too high estimate? Yeah, 1. So 100%. You could even have said something like 0.8, right? Any of that. Okay. So we're talking about just region A. Okay. Now, for number 4, and I actually repeated the graph over on the next page for you guys so you could have it. It says to approximate the area of region A, we're going to split that region into 10 rectangles. Okay. So A is referring to that entire region. It says one of the rectangles was shown in the example. What would be the width of each rectangle? Okay, well, it'd be 0.1, right? We're going from 0 to 1. Okay, so 1 minus 0, and we would divide it by 10, which is 1/10. Okay, so that's how we got it, the length of that entire region. If we were thinking about our intervals like we're used to doing, all right, B minus A over N, all right, B minus A over N. Okay, and then how could we find the height of the rectangle shown? How would we get this height? Yeah, we could do that. I meant to put this right here. That's the width. Okay, we could count, but let's say we weren't able to see it as good as we can, right? Because is it exact if we count? No, we're going to miss some stuff, right? So that was my width up there, sorry. If we're going to count, if we're going to find that, all right, where does it start at? Yeah, it starts up here, okay, at the top. And which curve is it on?
A.
It's y equals x, and this is L of x, okay? And so if we want our height, we're going to come over here to 0.7, is looks where it starts, minus the value of the curve down here, which is L at 0.7, okay? So that would give me my height. Another way to think about that, okay, so it would be about 0.510, okay? Another way to think about that would be the difference between these two functions. Okay, so we're going to get our height from the difference between the two functions. Okay. So now, we've learned in calculus throughout a lot of this, if we want to get an actual area, how many rectangles does it take? Infinite, okay? It takes infinite rectangles. So we're going to do an integral expression, okay? How long is my interval, not my integral, but my interval that we're talking about? It goes from where? 0 to 1, okay? We're doing area of a rectangle, and area of a rectangle is length times width, okay? Or base times height. So my height we got by taking x, which was my top function, minus L of x, my bottom function. All right, so this is top minus bottom, and then dx, which is my width, all right, b minus a over n. So this is my height, and this is my width, right? So that will give me area. And so anytime that we need to do area between two curves, it's really nice, okay? Your width is always dx. Your height is always top minus bottom. Now, tomorrow we're going to talk about functions that are defined a little differently, where we will do right minus left, okay? So to find that area. But for today, we're just doing top minus bottom. So let's say that we have a region. Let's look at this one. All right. We're going from A to B. We're going to do f of x. And we're going to do g of x. Okay. So we've got our two functions, right? And we want to find the area between those two. Okay. I like to think in terms of what would one rectangle look like. So I always draw that in there. You don't have to, but that's what I do, right? And so our area would equal the integral from A to B. Which function's on top? F of x, the blue one, minus g of x dx, okay? So if f is greater than g, it's going to look like that. What if it were reversed? It'd be g minus f, right? So whoever's greater, all right? Now, here's some things about this. The area must be bounded. Okay, so these are always going to be definite integrals. We're going to have intersection points. We're going to have things that we have to find. Okay, and this area is always positive. Okay, so if you're doing area and you don't get a positive answer, something happened. Now, why does it work that we can do top minus bottom to get the height of the region that we want? Okay? If we think about just the area, the integral of from a to b of f of x, how much area does that cover? Yeah, it covers all of that, okay? And do I need all of that area? Okay, then we talk about the area under the G curve. Well, that's this much, okay? And that's not enough. So how do I get what I want? I subtract the two, all right? So the total area of the blue minus the area that is extra, the G, gives me what I'm looking for in between, okay? So that's why it works. Right? Now, it'd be nice if our functions always behaved so nicely, right? But sometimes they do things like this. Okay. How many times they intersect this time? 3. Is the same function on the top in each spot? No. Okay. So if we're looking for the area between these two curves, it's going to take 2 integrals, right? Because it switches who's in charge, right? So my total area would be the integral from a to b. On the first one, f of x is dominant, so f of x minus g of x dx. I'd add to that the area from b to c. This time, g of x is dominant, so g of x minus f of x dx. Okay, so know that some areas, all right, depending on what it looks like, will require multiple integrals to make it happen. Okay? All right, so let me give you some strategies, all right, to help you solve these, all right, because it's a pretty straightforward process. All right. But some things that can help us get there, all right? So first, all right, you've got to find their intersections, and sometimes it will be obvious. Okay, that becomes your A and B. It may require you to graph or to do it algebraically. Right, so setting 2 functions equal and solving. The next thing we have to do is identify in our region who is the top and who is on the bottom so that we can get the correct integral. And then finally, we just got to integrate correctly. So there's going to be a little algebra in the setup, and then we just have to integrate it correctly, and life is good. We're going to start by looking at some where the graph is given to you, and then some where we'll have to find the intersection points. We'll do some with a calculator, some without. Rock and roll. Here we go. So let's take a look at this one. So we have the region R. In the first quadrant, it's enclosed by the graphs of y equals 3x and y equals x squared. Now, can you pick out which one is 3x? Yep. All right. This is y equals 3x in red. It's linear, and y equals x squared in blue. All right. Where do these two graphs intersect at? 0 and 3. Okay. Those are going to be our boundaries. So we're going to do the integral from 0 to 3. Right? Which function's dominant? 3x minus x squared dx. And then we're going to integrate. Okay, that is the setup. All right, this is a simple one to integrate, so we're just going to get an antiderivative. What would be the antiderivative of 3x? 3 halves, x squared, and then the antiderivative of x squared. 1/3 x cubed. We're going to evaluate from 0 to 3. We'll start with that 3, so it's going to give me 3 halves times 9 minus 1/3 times 27. Nice, when I put in 0, it's going to all go away. And so that would give me 27 over 2 minus 9, which is 18 over 2. So 27 minus 18, 9 over 2. Okay, too terrible? All right. Look at this one. It's going to give me a lot of information. All right. So y equals x squared plus 3, y equals x equals 0, and x equals 2. Okay. So it's given me this region right here. What are my boundaries that we're going to go between on the integral? Yep. 0 and 2. Those vertical boundaries that they told me. So 0 to 2. Which functions on the top or dominant? X squared plus 3 minus, and then the other function is x and a dx. Finish that one off. Helps if you write it correctly. Okay, yeah, it helps if you write the problem down correctly. Okay, x squared plus 3 and then minus x. We do our integration. Our antiderivative, 1/3 x cubed plus 3x minus 1/2 x squared. Plug in our 2. Gives me 8/3 plus 6 minus 2, or 8/3 plus 4, which will give me 20 over 3. Okay. So question about those two. All right. It's nice when they give me the whole region, they give me the whole graph, we can see it. Let's do one where they don't give me anything. All right. They just give me the algebraic expressions and we got to do all the rest. Okay. It says find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. First thing we need to do is to graph these. All right. What's the first one going to be? What's this shape going to be? It's a parabola. Which way does it open? Down. And how's it been shifted? Up 2. All right. So we're going to go up 2, right 1 over 1, right 1 over 1. Bless you. Right 2 and down 1, 2, 3, 4, just to give us some sense of what we're doing. 2, 1, 2, 3, 4. Right, and so there's my pretty picture. Okay, then let's do g of x, which is just y equals x, which is nice. Okay, so can you see where these intersect nicely on that graph? Yeah, it looks like they intersect at -2 and +1. Okay, now I want to show you the algebraic way to do that just as a reminder, okay? Because there are some times where our graphs are not going to be that nice. What we're going to do is we're going to take each of those functions and just set them equal to each other and solve for x. So 2 minus x squared would equal x. If I wanted to solve that, so this is just an alternate, okay, not required. That would give me 0 equals x squared plus x minus 2. I should be able to factor. So x plus 2, x minus 1, and we get -2 and +1, which was exactly what we got looking at the graph. Okay, so there will be ones where we have to do that, where the graph is just not we're just not gonna be able to see the intersection. Okay. So those intersections become our boundary. So we're going to go from -2 to +1. So this time we're not going to get a 0, all right, to use. It's going to be a little bit more complicated, which is the dominant function, the quadratic or the linear. Quadratic. So we're going to take 2 minus x squared, and then we're going to subtract the linear, which was x, and we're going to do all of that with respect to x. Okay. Typically, the integrals are not difficult, or the antiderivatives are not difficult when we do these, which is nice. And if they are, they let you use a calculator. So this is going to give me 2x minus 1/3 x cubed minus 1/2 x squared. We're going to go from -2 to +1. Be really careful when you evaluate here. Okay. So 2 times 1 would be 2, minus 1/3, minus 1/2, minus, and I use parentheses so I don't, or brackets so I don't mess up. 2 times -2 would give me a -4. -2 cubed would be a -8, so that would be plus 8/3. -2 squared would be a +4, which would give me a -2, right? We have to remember to distribute that negative to that second parenthesis, so I'm just going to keep all of my terms. 2 minus 1/3 minus 1/2 plus 4 minus 8/3 plus 2. And I do that on purpose just to help me collect like things, right? Let's start with the whole numbers. 2 plus 4 plus 2, that would give me 8. Minus 1/3 minus 8/3 would give me minus 9/3, which would be minus 3, and then minus 1/2. So this is going to give me 5 minus 1/2, or 4.5, which is 9/2. Okay, so just some arithmetic there. What do you think? It's okay? Good news, it doesn't really get that much grosser. Yeah, right? Grosser, is that a word? I don't know. If they work in a grocery, it is, but okay. Sorry. It's Monday and it's raining. And I missed out on a joke, so life is hard. All right. I could use a nap, so if y'all come in here later today, just keep walking.
I slept so hard.
Yeah, I did. All right, let's look at this one. All right. Still non-calculator. We're going to get to the calculator ones here in just a second. All right. See if you can do that one. It's going to cause you to think about your trig a little bit. We're starting paper plate trig in second block today. Is he conceding to you, Samuel?
A little.
Okay. It's good for him.
Don't spoil it.
Okay. Left hand, because it makes the first quadrant. The middle's pi over 4. Okay? All right, pi over 4, square root of 2 over 2, square root of 2 over 2. Square root of what's left? Pi over 6 is closest to your thumb, square root of 3 over 2 and 1/2. Pi over 3 is at the top, 1/2, square root of 3 over 2.
Oh, I see what you mean. For the boundaries, I wrote pi over 2 to pi over 4. Actually, I can recover from this.
He said, I can recover from this.
It's just the same thing, we just get more action.
Yes, ma'am.
Are you doing the thing where you add them together with the thing? I mean, do you do like, if it's a negative number, you add it with positives? Or you always,
I don't understand what you're asking me.
whenever you do the
Top minus bottom?
evaluate it,
Oh,
for the bracket,
yes. So it's plug in the first minus plug in the second.
always minus?
Always minus.
With 0.
Yeah.
Is it, yeah.
Yeah,
Okay.
I forgot to do the back.
so you referenced it like 5.
Sign of 0.
Yeah, we were
I think
just
I
like,
did, I think I remember.
Sign of 0. Cosine 0. Square root of 2 minus 1.
I saw that.
It's a minus. That's a minus.
You're so right.
I'm very excited for the.
All right, so let's take a look. Okay, we can see that our first intersections or the boundary starts at 0, all right, on our picture. But we got to find the other intersection, all right? This is a non-calculator question, so we've got to think, okay? How do I get, where is the cosine equal to the sine? In other words, where is the x-coordinate equal to the y-coordinate? What arc length family? Pi over 4, okay? That happens at pi over 4, so we had to know a little bit about trig, okay? If we look at the region itself, cosine is dominant. It's there on top, minus sine dx. And now we're going to take an antiderivative. When we take an antiderivative, what's the antiderivative of cosine? Sine. What's the antiderivative of sine? Negative cosine, but there's already a negative there, so what's it going to make it? Plus cosine. And we're going to evaluate from 0 to pi over 4, which means we're going to take sine at pi over 4 plus cosine at pi over 4, and then minus both of those together, sine at 0 plus cosine at 0. Okay, we get our values, square root of 2 over 2 plus square root of 2 over 2 minus sine at 0 is 0, cosine at 0 is 1. Now, I have two square roots of 2 over 2. How does that simplify?
Square root is 2.
Just square root of 2 minus 1, and that's an exact answer. Okay? This was 2 square roots of 2 over 2, which is just a square root of 2. Okay? How'd you do? Good. All right, let's do one more without a calculator. Then we're going to get to the calculator ones. They're my favorite. Okay. So on this one, let S be the region in the first quadrant bounded by the graph of the cube root of x and the horizontal line y equals 2 and the y-axis is shown here. Let's find the area of S. Where does this region start? 0. Where does it look like it stops? 8. Okay. Could we verify that and make sure? The answer is yes. And we would set the two things equal, right? How would I solve for x? I'd cube it, and so x is indeed 8. So if you're not sure, you can always set the two graphs, the two equations equal and solve. Okay? Which function's dominant? The y equals 2 minus, can I write that as x to the 1/3? Fine by me. Okay. Get your antiderivatives. What's your exponent going to be? 4/3. What's your coefficient going to be? 3/4. Good news, there's a 0 in there. Okay, so we're only going to have to worry about putting in that 8. Okay, 8 to the 4/3, what does that mean? Yeah, 8 to the 4th, and then you would cube root it, right? So how about we do the cube root of 8 and then raise it to the 4th? Okay, cube root of 8 would be 2 to the 4th would be 16. So I've got 3/4 times 16, which would give me 12. And 16 minus 12 would give me 4. Okay. What you think? Got it good? All right, let's do one with a calculator. All right, let's do one with a calculator. I'm going to show you a trick. What's the first thing you're going to need to know? Yeah, where they stop, right? We can see it starts at 0, so we know the integral is going to be 0 to something, all right? And we've also got to figure out which one is which in terms of the functions. Which one do you think is f of x? The top one, it is, okay? And then your x cubed function is the one below, right? So let's go over to our calculator. What's the nicest way to get an intersection? Graph them, okay? We're going to graph them. So we're going to go to y equals, and we're going to put sine of 2x in one. And then in the other, we're going to put x cubed minus 2x. Not that. Okay, and we're gonna, can you see that window? No. Just seems to see what happens. Okay, now we're only talking about this first little piece, it looks like, so I'm gonna kind of zoom in so I can see it. Okay. Second trace, we're going to find the intersection, which is number 5. Okay. Mine tells me to get to the left of it. Yours is just going to ask if this is the first curve and the second curve. All right. And our intersection happens at 1.464, something like that. Okay. So you have a couple of options here because this would be on a free response. Okay. You can go ahead and do the approximation 1.464. Okay, which is what a lot of people will do. All right, they'll just say that's 1.464, right, which is completely allowed. All all right? But something else people will also do, and I hope it works on this calculator, on my app, okay? I know it works on yours. Right now, that value is stored in X on your calculator, that 1.464, okay? So if you go back to your home screen, all right, I like to take X, so I'll hit, not that. I like to take X, and then I'm going to use the stow key. It's right over here next to 1 and 4. Okay, so I'm going to take that value, and I'm going to store it in another letter. Okay, and the reason we choose another letter is because sometimes you're going to have 2 intersection points that you need. All right, so you could call one A and one B. So if I stow this in A, so alpha math, it should say that number. Okay, and I'll show you why we do that here in just a second. All right, it just saves me from typing in so many things. Okay, so now we want to find the area of this region. Well, we know we can also write that as 0 to A, all right, which is what I just did, of f of x minus g of x dx. And as long as everything is in the calculator, okay, one thing they will give you, they will deduct points for is if you put on your paper y1 minus y2, don't put that. Put f of x minus g of x, even though we know that's what we're going to do on the calculator, okay? So if we go back to the calculator, okay, now we can do math 9, all right, 0 to, I can either put in 1.464, all right, or I can do alpha A, and it knows it's 1.464. Okay, we put y1, so alpha trace y1, not times, minus alpha trace y2, and the dx is there. And when we hit enter, it just does it. Right? So as long as you've got your equations in y1 and y2, they're there. You're not going to have to type it all in again, okay? You can store your intersection value in a letter, but you don't have to. You can just type it in 1.464, okay? But a lot of people, if it's a number you're going to have to use multiple times, it's nice to store it. That way you've got it. You can just recall it as a letter, and it knows, okay? So your correct answer, 1.983 or 1.984, all right? What do we think about that? Okay. All right. Last page, best page. Okay. So you take a second and see what you can do with A. Let's just do A. Find the area of R. It is calculator active, the whole thing. Anything weird about this one? Since you said it, we're gonna say yes. All right. Tell me one thing we're gonna have to know for sure. All right, where R and S, all right, where they intersect, where tan and 2 minus x cubed intersect, okay? Use your calculator, get that bad boy. Okay, and did you get 0.902? Okay. Now, I want you to look at this region R for just a second, okay? I'm going to highlight it. So we got region R right here. Is that tangent curve dominant over the cubic the whole time? It's not, okay? The only place it's dominant is up until we get to that 0.902, okay? Because then, what's the only curve I'm left with? The tan one, okay? The only thing I'm left with over here is the tan curve. It's no longer touching, I mean, not the tan, the cubic is no longer touching the tan curve. So it's actually going to take 2 integrals to do this one, okay? So the first integral we're going to do from 0 to 0.902. And in this one, tangent is dominant over the cubic. So we would do tan minus 2 minus x cubed, okay? And notice I put that in parentheses, okay? But that doesn't get the entire region of R, okay? It doesn't get the entire region. So what we're going to add to it is we're going to start at that 0.902. How could we figure out where to stop? It's the 0 of that cubic curve. Okay, it is the 0. So can we put that in the calculator and get that approximation as well? Yep. I have it exact right now, so let me figure it out. 1.25 what? 9. Let's just call it 1.259. Okay? So this is where if you were storing values, you might want to use an A and a B because we've got 2 different numbers we wanted to use. If you solve that out, it's the cube root of 2. All right, that's the exact answer. So to 1.259. And this time, the only curve I'm using is 2 minus x cubed dx. Okay. That one's hard. Okay, it's hard to see that we really do need to split it because that tangent curve, I mean the cubic, the tangent, all right, is only dominant. Wait a minute, I did this wrong. This should just be tangent. Let me stop. Let's go back. Sorry, y'all were looking at me like I was 4 kinds of crazy. Yes. All right, here we go. Tangent's all we got to start. There we go. There we go. All right. So here we've just got tangent that's dominant. And in the second piece, we've just got the cubic involved. Okay. That's better. All right. So it would take 2 integrals to do it. And so did you get, we should get 0.729? I believe. Right. So that's one way to do it. Okay. Now, is there another way to do it? You know there is. Okay. I'm going to erase what I've colored over here for just a second. All right. Let's see if we can come up with another way to do it. All right. We want R. Okay. What are some thoughts? What if we did S and R together? Then what would I need to take out? I would take out S. Okay, so another way to do that. So to not have to split that little R region, okay, it still intersects at 0.902 right here. It still ends at 1.259. Okay, so if I do the whole integral for s, that's going to be the integral from 0 to 259, sorry. And that curve is the cubic, 2 minus x cubed dx, minus what's going to be the integral of the s region. Zero to the intersection, cubic on the top, and s stops at the tangent. Okay, so that's the way to do that one. So you could do it that way as well. And for a lot of people, they're going to see that better, okay, than the fact that I can use two single integrals with just the r region itself. Okay. Should get the same answer. Okay, so you might want to double check yourself. They heard you were here. They're coming to get you. Ha! We live right next to the fire hall, so the stuff's always going out. Okay. And then the last one just says what would be the area of just S. Well, we've already done it. Okay, this right here will give you just S because we'd already done it. Okay, and I don't even have that final answer. I don't know what it is. Okay, so this is just region S. Okay, so this we did S and R minus S. All right, that's how we did that one. Okay, area between two curves, dominant minus the other one. Okay. All right, rock and roll. You need to practice a few of these, okay? So there's not very many. On page 408 and 409, we've got 12579, 17, 28, and 36. Okay, you do have a wrap up today, so let's do that. Get those points for today. We'll have 3 this week. Parker, you can go back and do all those ones from last week and just let me know when you're done, okay? All right, just a reminder, Quiz Wednesday. Eight, 1 through 3.